This is part 2 of chapter 9. We're going to actually begin in your guided notes on page 8. And in your slideshow, if you're following along with that, it'll be on slide 31. So we're talking about a problem here that we've been working in the first section. It says the management of Priority Health Club claims its members lose an average of 10 pounds or more within the first month after joining the club. Now there's a consumer agency that wants to check this claim, so it took a random sample of 36 members and found they lost an average of 9.2 pounds within the first month. The population standard deviation is given to us. It is 2.4 pounds. So we want to find the p-value for this test, and we want to make a decision if our alpha level is 0.01, and then we're going to talk about the same problem if our alpha level is 0.05. So let's take a look at our guided notes page and see if we can fill in some things. First of all, this health club claims its members lose an average of 10 pounds. That's going to be the mean that they claim. So that's going to be our old mean. And that's within the first month after joining. Now the consumer agency wants to check this claim. So the consumer agency is only interested in a problem. There's only a problem if members lose less than that 10 pounds. If they lose more than the 10 pounds, then the advertising is okay with our consumer watchdogs. So they took a sample. The sample is 36 members. And when they did that, they came out with a sample average of 9.2 pounds. So our X bar is 9.2 and our N is 36. Now, we were given the population standard deviation. So we don't have to deal with the sample standard deviation here. We're dealing with population. And remember, that allows us to use the Z table when we're looking up our numbers here. And then they told us our alpha level. Our alpha level is 0.01. So I think I've filled in the 5 items that we must be given before we can work these, checking these hypotheses. And now we can do some calculations on our own. Our first one, we always want to calculate the standard deviation. Now, since it's not the sample we're dealing with, I'm going to cross that out, and we're going to use the population standard deviation, the standard deviation of X bar. We have to take the population standard deviation, which is 2.4, and divide it by the square root of the sample size. When we take 2.4 and we divide it by basically 6, we're going to get the number 0.4. So we've got that. It's ready for when we have to calculate or do our Z calculations. Next, we want to state the hypotheses. Now, we want to state the hypotheses based on what they're telling us, and this is a little confusing in this problem. Remember, the consumer agency is only interested in a problem, or they're only going to say it's a problem if the members do not lose 10 pounds. That's the alternative hypothesis. That's what we set up first. We say, what if the mean is actually less than 10 pounds? That's the reason they're doing the research. They couldn't care less if it's greater than 10 pounds, and that's going to be the null hypothesis. If it's greater than or if it's equal to 10 pounds, the consumer agency is going to be okay. What they're looking for is to reject that null, though, and then say the members do not lose an average of 10 pounds. They lose less than that. We've already said, since we know the population standard deviation, we get to use the Z table. And now we're going to look at our rejection region for this. What we have to do is say our rejection region is based on the alternative hypotheses. In other words, since it is a less than, this is a left-tailed test. I'm going to set up my rejection region in the left tail, and it's going to equal the entire alpha area, which is 0.01. Now once I have that done, I can look up 0.01 on my Z table, and of course I'm on the negative side of Z here, and I'm going to see that it goes to a negative, let me see if I can find 0.01 as close as I can get. It's going to be right between these two numbers. So I'm going to say I'm going to go with the lower area, which is the 0.0099, and I'll say that's a negative 2.33. So on my Z table I found 0.01 is negative 2.33. That is my critical value for rejection. Now, I have the critical value. I know what I'm going to reject. I'm going to reject if I observe a Z value that is less than negative 2.33. Because remember, the rejection regions are always in the tail. The other thing that I might observe is I might observe a p-value. Now the p-value would have to be less than the alpha value, always the alpha value, and the alpha value in this one is 0.01. Well, I've got it ready. All I have to do now is find out what my observed value of z is. So I'll calculate this test statistic. I have a formula for that. It is the sample mean, the sample that I took, minus the population mean, or the old mean, and then I divide it by the standard deviation that I calculated, the 0.4. So I take 9.2 minus 10 divided by 0.4, and I come up with a z-value of a -2. Therefore, I can look up, for a -2z, I can look up the p-value, the observed p-value. Go back to your table and find out what the z-value is for a -2. -2, 0 is what it would be. And here's the number I want, 0.0228. So I've got 0.0228 is my observed p. I've got a -2 as my observed z. And remember, those are what I took the sample, and this is what they came out to be. So does that make enough of a difference for the consumer agency to reject the health club's claim that its members lose an average of 10 pounds or more each month? Let's look at our statistics and compare them. And this is how your decision rule will come in handy. Here's your decision rule. You said these two things were the decisions. You can sort of copy them down to here. I'm going to say observed z, which came out to be a -2. It has to be less than a -2.33. That was my decision rule that I set up here. But -2 is not less than -2.33. In fact, if I place my -2 up here on my graph, I'll find that it's in here somewhere. Here it is in blue, -2. And the area associated with -2, as we found out when we looked it up, is 0.0228. So now that's my test statistic in blue. And if I look at the p-value test, I say 0.0228 would have to be less than 0.01, which is alpha. And of course, it's not less than that. As you can see, it does not fall, the -2z value, the test case that we took does not fall within the rejection region. So our conclusion here is that we fail to reject the null hypothesis. Okay, let's do something else. Let's try something different. Let's say we change the alpha level. Let's say we change the critical value, or the critical level that we're looking at. So we're going to change it to 0.05 this time. Now, if we still have the same test statistic, so that's not changing on us, but what is changing is where our original z-value is. Where's our rejection region now? Now that our rejection region has to include a p-value of 0.05, I've got to find out where 0.05 is. If I look up 0.05 on my z-chart, I will see, let's see if I can find it real quick for you, I will see that 0.05 is going to be right between these two numbers. Well, that's going to take me at 1.6, and I'll go with the lower area. I'll say it's a -1.6, and go to the top here, and it's a -1.65. So, my observed v-value is a -1.65. Is that less than the observed z-value, the one I observed, which was a 2? Is my rejection region now, is my test statistic now within the rejection region? Well, you can draw it on your chart here. Here's my -1.65. There's my new rejection region, right? And it has a 0.05 p-value associated with it. So you can see it's bigger than the other two, so it includes all the other two. And it's out here, and yeah, now my test statistic is falling well within it. So this is, yep, it does work this time. It checks. And we can also do the p-value check. The p-value check is 0.0228, which was the test statistic, would have to be less than our new critical level that we're looking at, which was 0.05, and of course it is. In this case, we would be okay. We would reject the null hypothesis. So, with the same test case, it all depends. It depends on the critical level that you're interested in. What precision were they interested in when they ran the test? Now let's take a look at our next problem. This one talks about a telephone company that provides long-distance telephone service. According to the company's records, the average length of all long-distance calls that are placed through this company was 12.44 minutes. That was since 2015. The company's management wants to check and see if that mean length or that average length of the current long-distance calls is different from 12.44 minutes. And so they take a sample of 150 calls that are placed through the company, and this sample gives a mean length of 13.71 minutes. And they also note that they still have their population standard deviation of 2.65 minutes. They want to use a 2% significance level, and they want to see if they can conclude that the mean length of all current long-distance calls today is different from the 12.44 minutes that they found in 2015. So we're going to go to our note page on page 9, and we're going to look at this problem. First, we're looking for these 5 items that are written here across the top. We want the mean, the old mean, we want the sample size, we want the sample data, we want a standard deviation, population or a sample, and we want the significance level or the alpha level. So see what they told us. According to the company's records, the average length of all calls placed through this company was 12:44. So that's going to be our old mean. 12 minutes 44 seconds, or 12.44 minutes is what they had in 2015. They want to check and see if it is different from, and this is your keywords here, is different from 12.44 minutes. There's your alternative hypothesis. They want to say that the mean is different from, is not equal to, the old mean of 12.44. So if our alternative hypothesis says not equal, our null hypothesis has to say that it's equal. So we've set our hypothesis from the problem. Now they took a sample of 150, that is in, and this sample had a mean length of 13.71 minutes. That's our X-bar, our sample mean. There's population standard deviation is given to us, so we don't need the sample standard deviation. We have a population one, which is much better. It's 2.65 minutes, and they want a 2% significance level. Well, we know we have to represent that as a decimal, so it's 0.02. Now, we have to do a calculation because we know we're going to be calculating z. Let's go ahead and get it out of the way. We know we have to calculate the standard deviation of X bar. So we're going to take the standard deviation of the population, and we're going to divide it by the square root of the sample size. When we do this, we come up with a decimal, and 4 decimal places should be good enough for us, so we'll go to 0.2164. That's our standard deviation we're going to deal with when we calculate z, for the test statistic. Now we have to select a distribution. Do we use z or do we use t? Well, if we know the standard deviation of the population, we always use z. And then we find our rejection region. This is where we're going to lay this out on a standard curve here. Now we want to, this time we have to understand that they are saying the mean is not equal to, it is different from, it is therefore a two-tailed test that we're dealing with. We have to split our rejection region into 2 parts, and 1 part goes in each tail of the curve. So since we had an alpha level of a significance level of 0.02, we have to say 0.02 divided by 2 would give us each tail of the test. So we would actually have 0.01 in each tail. Now that we have that, we can look and find out what are these 2 z's. We know the rejection regions are in the tails, so our arrows are pointing to the rejection areas, but we need to know what this critical level is, or what is this critical index here. In other words, what's the starting point of our rejection region? Now what we do is on the negative side of our z table, and always going to be looking up on the negative side for these, we look 0.01. And we found that one before, so I think I know what it is. Let me see if I can find it real quick. I believe it's right here. 0.01 is going to be, I'm going to choose this area, 0.0099. It is a negative 2.33 is what it is. So this is a negative 2.33. And I know from experience that the positive will be the exact same number but opposite sign. So it'll be just the opposites. My z's plus or minus 2.33 is what they are. And that is the z that I have for my rejection region. In other words, that's the one I've set up for the test. Now I'm ready to look at my sample, to actually look at my sample and see if I can figure out what it is. But here's the decision that I'm going to go ahead and write down. If I'm going to reject the null hypothesis, if observed z is less than negative 2.33, in other words, it would be pointing in the less than direction or in the negative direction here, or I would have to reject it if it is greater than a positive 2.33. So I have two rejection regions. I have to sort of make two statements here for observed z. The p-value statement, however, is pretty simple. I'm going to reject if the p-value is less than alpha. In other words, the entire alpha, the significance level up here. So 0.02 is what I will reject if the p-value is less than alpha. All right, now let's do some calculations. Observed z is my test statistic. I take 13.71, which is my test mean, my sample mean. I subtract the old mean, which is 12.44, and then I divide it by the standard deviation, the one I calculated, which is 0.2164. And I come up with my z value of, and it's pretty big, it's 5.87. And as z's go, that's a rather large z value. So my observed z is way over here. I don't need this side of my test because my observed z didn't fall into the negative range. It's going to be over here in the positive. And look, it's way over here. Remember that once I get past the number 3 standard deviations or 3 z's, everything out to this side in the tails is practically 0 anyway. So when I've got 5.87, when I say what's over here past it, it's 0. The observed p-value is therefore 0. Now, because it's a split-tail test, I would have to multiply that observed p-value by 2 to get the total, but still 0 times 2 is still 0. So my observed z, my observed p-value is 0. My observed z, my test statistic gave me a z of 5.87. So let's do the comparison. Observed z, 5.87, has to be less than, greater than, because I'm working on this side of my curve. So I'm not going to use this part of the test. I'm just going to use this one. Greater than 2.33. And 5.87 definitely is greater than 2.33. As we can see when we drew our picture, it falls into the rejection region. Okay, let's also do the test for the p-value test. Our observed p-value is 0. Check. Is that less than our critical level, our significance level of 0.02? Well, yes, it is. So by both of our tests, we find that we are supposed to reject the null hypothesis. Now let's look and do one more problem that's dealing with population standard deviations, and then we're going to shift gears a little bit and do 2 more types of problems before we finish. This one is on slide 41. It talks about the mayor of a large city who claims that the average net worth of families living in his city is at least $300,000. So there was a random sample of 25 families that were selected, and their net worth was $288,000. We want to assume that all of the net worth of the families in the city has a normal distribution, and we do have a population standard deviation given to us of 80,000. Using a 2.5% significant level, we're going to see if the mayor's claim could be considered true or false. So let's grab page 10 of our guided notes and let's take a look at the claim. Well, first of all, we're looking for the 5 items: the old mean, the sample size, the sample mean, a standard deviation, and a significance level that we're working with. That has to be given to us in all of these problems. So we look and we see that he claims the $300,000 net worth, and that's what we'll use as the old mean, because that's what the comparison is going to be about, is whether the mayor was wrong or right. There was a sample of families taken. There were only 25. Now remember, if we don't have a sample size of at least 30, we have to have a normal distribution before we can use our z-table, but we have already, that's why they told us this about a normal distribution, so we're okay even with a small sample size. The sample X bar, the sample mean that we took, turned out to be 288,000. And of course, you do have the population standard deviation given to you. It is 80,000. And the significance level we want to work with is 2.5%, which is 0.025. We'll go ahead and do this calculation because it's easy, and we know we're going to need it later, and it is the standard deviation of X bar. So we'll take X bar, we'll take the sample mean, we'll subtract the old mean, or what the mayor states is true, and we'll divide it by, sorry, this is not what I'm trying to do, sorry guys. We'll take the standard deviation of the population and we'll divide it by the square root of the sample size. That's much better. So really we're taking 80,000 and dividing it by the number 5, and we come up with 16,000. All right, let's look at our hypotheses here. The mayor claims that the net worth of his families is at least 300,000. So what we're trying to see, if the mayor's claim is false, we want to see if they are less than 300,000. That's how we set the alternative hypotheses. We set it based on what we're trying to prove, and we're trying to conclude that the mayor's claim is false. So the other side of that is the mayor's claim is true, and his people do have a mean net worth of at least 300,000, which would be 300,000 equal to or greater than $300,000. Which distribution? Well, once again, we do know the standard deviation of the population, so we get to use the z-table. We're going to look at our critical region now, and we're going to draw our curve, or draw a rejection region based on alpha all by itself. We don't have to split it in two because we have a left-tailed test. So here's my test, or here's my rejection region. It's in the left tail. And notice that it does follow the arrow in the alternative hypotheses, okay? So that's one way you can check yourself. It's in the left tail, and we want it to cover our entire significance level of 0.025. So now I have to find what z-value is associated with 0.025. Go back to my negative side of my z-table, and I look for 0.025, and fortunately that's one of those that I've done before, and I can find it pretty easy. Here it is, 0.025. When I look at the numbers, it's negative 1.96. So negative 1.96 is my z associated with my critical level. That's going to be the boundary of my rejection region, is negative 1.96. So what's my rule going to be? I'm going to reject the hypothesis if I observe a z that falls into this area. In other words, it would have to be less than negative 1.96. And the p-value always has to be less than. And this time my p-value is less than my alpha, which is 0.025. So that's my checks. Those are my rules. That's what I'm going to look for when I do my calculations. Now I'm going to calculate observed z. Here's where I get to do the calculation I wanted to do a few minutes ago. I take the sample mean and I subtract the old mean, and then I divide it by the standard deviation that I calculated, which was 16,000. These numbers just have lots of zeros in them. And when I do that, I end up with a z of negative 0.75. That's my observed z. That's what the sample tells me z would be. What's the p-value that's associated with a negative 0.75? Well, that's not too hard to look up. Negative side of the table, and I go to 0.7, and I go over until I'm in the column for 5. And here it is, 0.2266. So I have my observed p-value, 0.2266. Now, here's my comparisons. Once again, comparisons are based on the decision rules that I wrote out earlier. I want to see if observed z, which is a negative 0.75, I want to see if it's less than negative 1.96. And I want to also check and see if observed p-value, which is 0.2266, is less than 0.025. Well, a negative 0.75 is really not less than a negative 1.96. Let's place it on our graph up here on our curve, and you would see a negative 0.75 is like is below a negative 1, isn't it? Or above a negative 1. And the area, the 0.2266, is much bigger than the critical level that I was dealing with. So I think I rejected on both counts. So here's my conclusion. I failed to reject it on both counts, sorry. So here's my conclusion. My test fails, so I fail to reject the null hypotheses. Now let's change gears just a little bit and let's talk about where we do a hypothesis test about the mean, but this time we don't know the standard deviation of the population. Now remember, we always have to have some standard deviation given to us, so this time what we're going to have is a standard deviation of the sample, or a standard deviation of X bar. So we're going to still calculate the test statistic. This time we have to use the t-table though. So the calculation for the test statistic t is going to be exactly the same, or it's going to look the same as it did when we were calculating for z. We're going to take the sample mean, subtract the old mean, and divide by the standard deviation that we calculate. This time, that calculated standard deviation will simply take the standard deviation of the sample and divide it by the square root of the sample size. Now this is also called, when we calculate it, we will call this the observed value for t. So instead of having observed z, this time we're going to have observed t. Not too much of a change there. So let's look at this problem. We have a psychologist. He claims that the mean age, or the average age at which children start walking, is 12.5 months. Well, Carol wants to check this, so she takes a random sample of 18 children, and she gets a mean age at which these children started walking. She finds it was 12.9 months. And she doesn't have a population standard deviation, so she takes the standard deviation for the sample, and she finds that's 0.8. Now, it is known for our purposes that the ages at which all children start walking is approximately normal. Now, we need to know this because we only have a sample size of 18 children, which is below 30. We're going to find the p-value, which we're going to find for this test, of the mean age at which all children start walking. We're going to see if it is different from 12.5 months. And we're going to make a conclusion on this claim the psychologist claimed based on a 1% significance level. So here's our problem, and we're on page 11 of our note pages, and we want to see if we can find the 5 items that we always have to find in every problem. So we're looking for the old mean. Well, that would be the psychologist's claim of 12.5 months. And then we need a sample size. Well, we know Carol took a random sample of 18 children, and her average age that she found when she did that was 12.9. So we've got our X bar, we've got our sample mean. We don't have the population standard deviation. We have to deal with the sample standard deviation. Remember, that has the notation of S instead of sigma. So we have a standard deviation here of 0.8, and we want a significance level of 1%, which is 0.01. Now, once again, we don't have the population standard deviation, so we will be calculating the standard deviation of the sample for the sample mean. So we'll be S of X bar, but we do it the same way. We take the standard deviation of the sample that we have, which is an 8, not an S, and we divide it by the square root of our sample size. So it's calculated exactly the same way we did for our population standard deviation. And we get some decimals, 0.188, and we'll just go to 4 again. 0.1886 is good enough. Now let's take a look at stating our hypotheses. Usually that's what I do first, but this time I skipped around some. What does Carol want to know? She wants to know if the age the children start walking is different. She wants to know if the claim is true. She doesn't really care if it's higher or lower. She just wants to know if it's different from what the psychologist claims. So she wants to know if the mean is not equal to 12.5 months. That would be Carol's alternative hypothesis. What's the null hypothesis? Well, the null hypothesis is that the claim that the psychologist made in the beginning was true, and the mean age that children start walking is 12.5 months. Which distribution? Since we don't know sigma, since we only have S, we have to deal with the t-table. So now let's look at our critical region. First, we have to define our rejection regions. Because we have not equal in the alternative hypothesis, we're going to have to split this and have a rejection area in each tail. We do this the same way we did it for the t-table, but I'm just going to note that we're going to be getting t-values down here instead of z's. So we take our alpha divided by 2, we take our significance level that we wanted of 0.01, and we divide that by 2, and we get 0.005. So we'll place 0.005 in each tail and split our rejection region because we're interested in either high or low areas. If it's either too high, if it's a lot higher than 12.5, or if it's a lot lower than 12.5, we're going to reject it. All right, now I need some t-values for this. And t is different. You remember there's only one parameter that we really have to have for t, and that is degrees of freedom. We have an n, a sample size of 18. So we would say n minus 1, or 17, is going to give us the degrees of freedom that we need for our t-table. So looking at my t-table, I have the degrees of freedom down here to the left, and I'm going to go down until I see 17. And then I'm going to go across until I find the significance, the alpha level, the significance level that I'm interested in. Now, since I've split this thing into two pieces, what I'm looking at is 0.005. I have to go all the way over here to the fifth column, almost to the last column. And I come up with a t-value of 2.898. So t, 2.898, remember t has 3 decimals where z only has 2. And look, I've split it in 2 places, so I know I'm going to have a positive and a negative value. This would be negative 2.898, and this one's going to be positive 2.898. So I've got it set up. I know exactly where I'm going to reject my sample, or I'm going to reject the null hypothesis if it falls into the rejection region. So now I have to come up with what my statement's going to be. I'm going to reject if observed t is either less than negative 2.898, or if it is greater than positive 2.898. Remember, that's because I have the split rejection regions. Also, I'm going to say my p-value would have to be less than, remember, it's less than the alpha value, which is still 0.01, even though we split it into 2 pieces. It's still the same thing for rejection, our rejection rule. Now we're going to take a look at what our observed t is. We calculate this the exact same way we calculated observed z. We take the sample mean, we subtract the old mean, or the psychologist's claim, and then we divide by the standard deviation that we calculated. 0.1886 is what that is, and we come up with a t-value of 2.121. I'm just going to round all t-values to 3 decimal places. Now, I need to find out what the p-value is associated with a t of 2.121. This is not as easy as it may sound. I still have to stay with my degrees of freedom of 17. So I can only use this one row right here. So I'm going to stay with my 17, and I'm going to say, where is it? 2.121, 2.11, 2.1567. I'm really close to this number. I'll never be exact with it, but I'm really close to this number, and I'm going to use that area, which if you can see at the top is 0.025. Let me see if I can move that down for you. I was on degrees of freedom of 17. 2.121 is really right in here somewhere. It's really close. And there's the area under the curve, under the right tail, which I can use that still. It's 0.025. Okay, so I know my rejection area, my p-value is going to be 0.025, but I also know that I have to take my p-value this time and see if I can set it up in my curve here. So where did this fall? In rejection or not rejection? Well, my t-value turned out to be positive, so I don't really need this test over here. I don't need the negative side at all. I'm just going to look on the positive side. I'm going to place a t-value of 2.121, and it does not seem to be falling into my rejection region. This will be 2.121. And what's the p-value that I said was associated with 2.121? It would be 0.025. Now, that's associated with 2.121, but if I want to do a p-value test and I have a split rejection region, I have to multiply this value by 2. And 0.025 multiplied by 2 would give me 0.05. So that's my observed p-value, because it has to be, I have to take into account both sides, even though I only need one side. So what's my comparison? It's going to see the same as I set up here. My observed t-value, 2.121. I would be checking to see if it was greater than 2.898, and it's not. And then I'm going to look at my observed p-value, which is 0.05, and see if it's less than my significant value, my alpha, which my alpha for this one, 0.01, and it's not. So what do I do with this decision? Well, I fail to reject. So Carol is not going to be able to reject the psychologist's claim that children start walking at 12.5 months. Now let's take another example that deals with the standard deviation of the sample. And it's the Grand Auto Corporation producing auto batteries. Now this company claims that its top-of-the-line never-die batteries are good for about, at least it says, 65 months. But a consumer protection agency tested 45 of them, and it found that the average life, or the mean life, of these 45 batteries was 63.4 months. And it did have a standard deviation of that sample of 3 months. Now, we want to find the p-value for the test that the mean life of these batteries is less than 65 months, because that's what this corporation, this consumer agency, is interested in. It's interested in finding out if Grand Auto claims about its batteries are not true, so they could get them for false advertising, so to speak. So we're going to make a decision, or a conclusion, come to a conclusion based on a significance level of 2.5%. So let's take our note pages on page 12, and let's see if we can find the 5 items that we know have to exist in every problem. We're looking for the old mean. That's going to be the claim that Grand Auto Corporation makes. They claim that their batteries are good for at least 65 months. So that 65 months would be their mean. The consumer agency tested 45 of them. That's our sample size. And it found the mean life of the sample was 63.4. So that's our X bar, our sample mean. We don't have the population standard deviation, so we have a sample standard deviation of 3 months. Remember, if it's talking about the sample and it says the average is in that sentence and then it keeps on going and says standard deviation, that is a sample standard deviation, not a population. They'd have to tell you if it was population. Now, they want us to look at a significance level of 2.5%, so we'll represent that as a decimal, 0.025. We're going to go ahead and do our calculation for our standard deviation that we need for the t-table, and that's going to be the sample standard deviation, or the sample standard deviation of X bar. The way we do this is we take the sample standard deviation and divide it by the square root of the sample size, and we come up with 0.4472. We will go to 4 decimal places again. Let's look at our hypotheses. What are we interested in proving? We're interested in proving if the mean life of all such batteries is less than 65 months. That's going to be our alternative hypotheses. We want to know if the mean is less than 65. Well, if the mean is equal to or greater than 65, the consumer agency has no problem. So that would be our null hypothesis. It can be either greater than 65 or equal, and they're okay. We have to use the t-table because we only know S. We don't know the standard deviation of the population. We're going to find our critical region by taking our alpha, and this time we don't have to divide by 2 because we have a left tail test. So here's our test. It's in this left tail here. And the area that's represented in the tail by the rejection region is the significant level or the critical level of 0.025. We have to find what t value is associated with 0.025. Now for this t-table we got to get degrees of freedom. So we take n and we subtract 1 and we get degrees of freedom is 44. Now let's go to our t-table, and then we have to go to the second page of it to find degrees of freedom of 44. And we are interested in this one row right here where degrees of freedom is 44. And what is the significance level? What's that area that we're interested in? It is 0.025. So I'm going to go over to the 0.025 column, and I find my t-value of 2.015 is what I'm interested in. Now I have to say that t-table is only giving me positive t-values, but I can tell that this is on the negative side of my curve. So I'm going to draw a negative and place it as a negative 2.015. And t, the only t I'm interested in, is the negative this time. It's just something you have to learn with t. So we're going to reject if the observed t-value is over here in this rejection region. If it is less than a negative 2.015, we will reject. And if the observed p-value is, of course, less than alpha, is our other test that we can do. If either of those was true, and they should either both be true or both be false. We're doing two just to sort of check ourselves. So now we have to find observed t. Observed t, we'll find that from our sample of 63.4, and then we'll subtract the mean that the company has of 65 months. And then we'll divide by the standard deviation that we calculated of 0.4472. When we do that, we end up with negative 3.578, 3 decimal places for t-values, remember. And now we are looking at the t-value associated with that negative 3.578. Well, t-value is a little tricky. You still have to stay with the degrees of freedom row that you were using. So I'm using this one row. That's all this one row is all I can look at is the row 44. I can go and I'm looking for a 3.578, and I go all the way out. I always look for a positive value. It has to be past this number. Well, if you note, these areas get smaller as I go to the right because I've got 0.005, 0.001. If I'm going to keep going to the right and I go past this number to get to 3.578, and remember with t's, if it's negative, it only shows us positive, so we just translate it to positive. We use the opposite. I'm going to have to be less than 0.001. So what's the area that I'm interested in? Well, this observed p-value is less than 0.001. In other words, it's really small. All right, let's take our comparison and see what we've got, all right? What have I got? I say my t-value, my observed t, a negative 2.015. It has to be less than my, sorry, that's the wrong one. My observed t-value of negative 3.578 has to be less than the t-value of negative 2.015. There you go. Okay, and a negative 3.578 would be less than. It would fall somewhere over in here. A negative 3.578 standard deviations is way over, isn't it? And then what is this area that I'm interested in over here? Well, here it is. It's less than, isn't it? It's smaller than, I can call it 0.001 if I want to, but it's really, really tiny. It is past 3 standard deviations, so it's really almost 0, isn't it? So I would look and say, is that p-value, the observed p-value 0.001, is it less than my alpha of 0.025? And as you can see, both of these checks that we've done say yes, we can reject. They fall into the rejection region. Both of our tests are satisfied. We can reject the null hypothesis. In other words, the auto corporation claims that their batteries are good for about 65 months, but the Consumer Protection Agency is going to reject that claim. Now let's take a look at one final example using the t-table or using standard deviations that are from the sample. And this one is about the Massachusetts Savings Bank. It's always concerned about the quality of service it gives its customers, so it had an old computer system where a teller could serve about 22 customers per hour. That was their average, that was their mean. The management noticed that at this service rate, the customers were waiting too long, so they got a new computer system in the bank, and they think it's going to increase the service rate. In other words, they're going to be able to serve more customers per hour, making the customers happy, and they won't have to wait so long. So let's take a look at the information that we've got here. And first we're going to say that the old mean that the bank knew was that they served 22 customers per hour. So that's their old mean, their old average. And let's see what the sample size they took was. So you can consider the new computer system. They took a random sample of 70 different hours is what they did. So they got 70, they're serving customers per hour. They take a sample of 70 hours. That works for our sample size. They found during these hours, the mean of customers served was 27. That's their sample mean. And they had a standard deviation. Notice they didn't say anything about population in there, so it is the sample standard deviation of 2.5. They want to know if this is really more efficient. They want to use the 1% significance level. We'll say alpha is 0.01. We've got to use the standard deviation of the sample, which we can calculate pretty quickly. 2.5 divided by the square root of the sample size, and that gives us 0.2988. All right, what's our hypothesis going to be? Well, we want to know if the mean is actually better with the new system. So we want to know if we have improved. We want to know if the mean is greater than the old mean of 22. Now, what if the mean is not? That would be the no change part of it. Nothing had changed. The mean would still be 22 or even less than 22. We have to use the t-distribution because we don't know the standard deviation of the population. We have S instead of sigma. And then we have to find our rejection region. Now this time I've got a right-tailed test. Notice my alternative hypothesis is pointing to the right. So my rejection region is going to be in the right side of the curve. And I've got a t-value that I've got to associate with 0.01, and then I got to find my degrees of freedom. Since my sample size is 70, my degrees of freedom would be 1 minus that, which is going to be 69. So let's find out what t is going to be for my rejection region. Degrees of freedom, take your t-table and go to find 69. Now 69 is way down there. See if I can get to it. And 69 would be right here, is this particular row. And once I have the row of 69, I know I have to look at my area under the curve. Well, in this case, my alpha is 0.01, and here's the 0.01 column. I'll just bring my finger down so you can see it. 0.01 and 69, here's where they meet up. The number is 2.382. So my t-value is 2.382. Now remember, with t, it only gives us positives. We have to decide if we're dealing with a negative or a positive based on how we drew our picture in our curve, and we're dealing with a positive this time because we have a right-tailed test. So we have a t-value of a positive 2.382. Our rejection will happen if we observe a t-value that is greater than 2.382, or it would happen if we had a p-value less than the alpha of 0.01. So those two tests are in place. Let's see what our sample tells us. We have a sample of 27. We're going to subtract our 22, which was the old mean, and then we're going to divide by the standard deviation, the one we calculated, 0.2988. When we do this, we come up with 16.734. That's our new t-value. Now, 16.734 is going to be way off the charts as far as standard deviations from the mean. So I'm going to put it over here just so you can see what I'm dealing with. 16.734, just think for a minute, what p-value do you think is going to be associated with that number? It doesn't look like there's going to be anything over there. In fact, I think we can pretty much conclude that there's not going to be, but let's look it up on the table just because we want to. We still have to stay with that same degrees of freedom of 69. So I have to go to my 69 row, and I have to say I'm interested in 16 point, well, I only get to, the largest number I get to is 3.213. And that's with an area of 0.001, which is small. So I know it's got to be a lot less than 0.001. You notice when I keep going as I go to the right, these areas under the curve get smaller. And that's what our picture showed us, right? So it's a lot less than 0.001. I don't know how much less than, but I can say it is a lot less than 0.001 and practically zero, wouldn't it be? We could say that from past experience, what we know about the areas under the curve past 3 standard deviations. Okay, so now let's write our test statistic down. My test statistic, my observed t, which was 16.734, would have to be greater than 2.382 if I want to reject the null, and it is. My observed p-value, which was, I'm going to just write it as less than 0.001 because it's so small, it would have to be less than 0.01, which is my alpha, and it definitely is. So my conclusion is I will reject the null hypothesis, which is great news for the bank. It means that their customer service system with their new computer system is serving customers well, and they've got a much better average than they used to have in how many customers per hour they served. Now, the final type of problem we're dealing with in Chapter 9 is dealing with proportions, and you knew it would be. We did population problems, we did sample problems where we knew the population standard deviation, where we knew the sample standard deviation, and now we're going to deal with proportion problems. So we have a test statistic that we use for proportion problems. It is always z. So we're back to the z table again. We call the sample proportion p hat, just as we always have, and we use the calculation for observed z. We say p hat, which is the sample proportion, minus the population proportion of p divided by the standard deviation of the sample proportion, which we can calculate using our old formula. That's the square root of p times q divided by n. Remember that when you have p, the population proportion, q is 1 minus p. And then n, of course, is the sample size. So these are the same formulas that we've been using in Chapter 7, and we've used some in Chapter 8, and now we're going to use them again in Chapter 9. So what is the value that what do we call this? Well, once again, we're going to call this the observed value of z. Here's our problem that we're going to work with first. We have a Gallup poll, and it was of traditional college graduates, and this is traditional as those who earn their degree before age 25. And these graduates, the polls show that 20% of these were emotionally attached to their old university or where they graduated, their alma mater. Suppose this is true, this is a true result for this population, the 2014 population of traditional college graduates. And then there's a recent random sample of 2,000 graduates that's taken, and it says that 22% said they're emotionally attached to their alma mater. We want to use a 5% significance level, and we want to see if we can conclude that the current percentage of traditional college graduates who are emotionally attached to their alma mater is different from the 20%. So let's go to page 14, and let's see if we can look at this problem and find those 5 elements, or really there's a few more here with a proportion problem that we have to be able to work the problem. One thing I want you to do with proportion problems is get rid of the field that says the mean is equal to, because we really don't have the mean anymore. What we have is the proportion of the population, which is listed here as p. So let's go back to our problem and see what it says. According to this poll, 20% of those who earned their degree before 25 were emotionally attached. Well, now that's going to be our population proportion. If I know my population proportion, I can say 1 minus p, and I can get q. So I'll go ahead and do that. Now they're saying that's true of the population. That's how I know it's a population proportion. Now there's a recent random sample of 2,000. So I've got 2,000 that they sampled, which is a really large sample. And of this sample, 22% said they were emotionally attached. That's the sample proportion, so that's p hat. I want a 5% significance level, so alpha for me has to be 0.05. Now, everything is pretty much in place, and I can go ahead and calculate my standard deviation of the proportion, and it's always calculated using the square root of p, 0.2, times q, 0.8, and then I have to divide by the sample size. And remember, all of this has to be done under the radical. We've done this calculation, used this formula before. It's the same formula, but you're going to have to do all of that in one step. Be careful with your calculator. Make sure it is doing all of it together, and it's not splitting things up and taking some of it out from under the radical. You'll have to watch where it puts parentheses. When I do this one, I get 0.0089. I'm going to just go to 4 decimal places again. Let's see if we can write our hypotheses. We'll start with the alternative. What is it they want to conclude? Well, the study is being done to see if they can conclude if the current percentage who are emotionally attached, and here's my keywords, is different from 20%. So they want to see if the mean is now not equal to 20%. Remember, that makes it a two-tailed test. What would the null be? Well, the null would be that the mean was equal to 20%. I'll say 0.2. All right, let's go now and see if we can figure out which distribution are we going to use with this. Well, this is a proportion problem. We always use z. You don't have to think about it. If it's proportions, you use z. Now, guys, once again, how do you know it's proportional? Look at all these percentages that we're dealing with. The percentages alone tell you that you're dealing with a proportion problem. What are percentages? They're really just fractions, and that's what proportions are too. So we're going to find our critical areas, our rejection areas. Remember, because it has not equal, we have to have a two-tailed test that we're dealing with. So we'll have rejection areas in each tail of the curve. We'll set them up. We'll say alpha, which is 0.05, divided by 2 this time. We have to do that. And we'll get an alpha divided by 2 of 0.025. That's what we can put on each side. So, what's the z associated with an alpha of 0.025? For z's, look these up on the negative side of the table. It's just so much easier. I can look up 0.025. I've done this one so many times, I think I can find it really quickly. And here it is. It's 0.025. It is negative 1.96. So I know I have to have a positive and negative, because I have a two-tailed test, 1.96 before I can make this work. So I'll say my negative 1.96 is over here. My positive 1.96 is over here. And these are my rejection regions. And I'm ready to set up my decision rule. I'm going to reject if the observed z value for the sample is either less than a negative 1.96 or if it is greater than a positive 1.96. It can be in either side, and I would reject. Or, here's my p-value test. P-value would have to be less than the alpha level, not alpha divided by 2, but alpha of 0.05. So, I'll calculate observed z. What is my z for the proportion that I observed? Well, I observed the sample, 0.22. I subtract the population proportion, 0.2. I'm going to divide by the standard deviation that I calculated. This should look just like what we've been doing for all the problem types. And when I do that, I end up with 2.25. I end up with a positive z. So I really don't need the negative side of the table. I really don't need the negative test, do I? I'm going to just deal with this positive test over here because I have a positive z. Also, I end up with an observed z value for this positive z. Well, now where is my positive z? It's over here somewhere, isn't it? The one that I observed is 2.25. Here it is. I can already tell that it's falling into the rejection region, but I'm not sure, so I'm going to double check myself every step of the way. Where is 2.25? And I'll look up the negative 2.25 because I only want the area in the tail. That's why I stay on this negative side of the table. 2.25 here's a negative 2.2. And if I go over to 5, here's the area I get, 0.0122. Okay, that's the area that's in this tail. Now remember, z only gives us the area to the left. So if I look up the negative z, it'll be like flipping it over to this side and looking up the area in the tail, and that's what I want. That's why I'm only looking up negative z's for these problems. They give me the area in just one tail. I just have to flip it around if I'm using a positive z value. Okay, so for the observed z value, observed p-value, I've got 0.0122, but wait a second, I have to multiply that times 2 because I have a split rejection region. So I'll multiply that times 2 and I get a observed p-value of 0.0244. That's what I'm going to look at my test for. Okay, I'm pretty sure it falls in the rejection region, but let's compare it. I was going to reject it if my observed z, which was 2.25, was greater than 1.96, and it is. I was also going to reject it if my observed p-value, which I calculated to be 0.0244, was less than my alpha, which is 0.05, and it is. So I feel pretty safe in saying I can reject the null hypothesis. Now another proportion problem that we've got says that machines that are used to make chips for calculators don't produce more than 4% defective chips when they're working okay. When the machine does produce more than 4%, it has to be adjusted. So the company is constantly checking, right, to see if the machine is working properly. And they have a quality control department, and they take samples of these chips and they inspect them to see if they're good or they're bad. And so they took a random sample of 200 of these chips, and out of these 200, 12 were defective. Now, they want the p-value to test the hypothesis of, the machine needs adjusting. So they want a conclusion. They're going to say they're happy with a significance level of 2.5%. Now, we know we're dealing with a proportion problem because it's got percentages all in it, but it's missing one very important percentage, and that's one that they're going to make us calculate. But let's look at what we do have. First, let's get rid of this mean because proportion problems don't need the mean anymore, and let's see what we do have in this problem. It tells us that they took a random sample of 200 chips, and it tells us that they are okay with their standard proportion of the population being 4% defective. So that's going to be a 0.04, and that's going to be the population, what we call the population proportion. That's the old one, that's the existing proportion that we're dealing with. Now once you've got that established, you have to ask yourself, what is the proportion of the sample? Well, they took and found a sample of 200, they found 12 defective chips. Basically, they didn't give us a percentage, but we can find it. 12 out of 200 are defective. If I do that and divide 12 divided by 200, I'm going to get a p-hat, or a sample proportion, of 0.06. So now I've got my sample proportion, I've got my old proportion, my population proportion we'll call it, and then I need q, which is going to be 1 minus p. So q in this case is going to be 0.96, and then the 2.5 significance level is going to give me 0.025. Go ahead while you're doing this and calculate the standard deviation of the proportion, because you know you're going to have it. It is the square root of p times q, and it's going to be divided by n, and all of that is under the radical. When I do this and go to 4 decimal places is fine. I get 0.013, and I'll round to 9. Okay, so it's 0.0139. Let's look at our hypothesis. What is the company interested in? Well, it's interested in making adjustments if it has more than a 4% defective rate. So it's interested in seeing if the mean, or the average rate of, the proportion is greater than the 0.04. So they're okay. They don't want to do anything if the mean is 0.04 or less. So which distribution? We're dealing with proportions. We have to use the z-table. How do I do it? Well, I've got a right-tailed test, so I'm not going to need alpha divided by 2 this time. I'm going to just set up my rejection region in the right tail of my test. I'm going to put the entire alpha value of 0.025 over there. I know I need a z-score of an alpha of 0.025. I know we've done this lots of times, but let's go find it again. A z-score of a z-score associated with the level under the curve of 0.025 is right here. It's negative 1.9, and I go to the top column and get the next digit, and it's 6. So I've got a negative 1.96. However, I just looked up the negative part of it because I just wanted to go the area under the tail. So I know I'm dealing this time with a positive 1.96 because I know which side I'm on. I'm always on the right hand side if my alternative says greater than, right? Okay, so now I've got this set. I'm going to reject the null hypothesis if observed z is in this area. In other words, observed z would have to be greater than 1.96. Or observed p, once again, would be less than 0.025. So I've got that pretty much set up. Let's see what I have when I calculate my test statistic. My test statistic calculated the same way. I had a sample, 0.06. I'm going to subtract my population, or my old mean, and I'm going to divide by the standard deviation that I calculated. And I end up with a z-value, 1.44. Now, 1.44, if I just look at this curve, looks like it's going to fall outside of the rejection region, doesn't it? What's the area associated with it, just so I can do the check on that? Well, I would look up a z of negative 1.44 because I only want the area in the tail, so that's why I'm trying to make it easier on myself and look up on the negative side. I'll go negative 1.44 and I get 0.0749. So 0.0749 is what this area is. It's definitely bigger than my rejection region, isn't it? So it looks like both tests are going to fail on me. But let's see what I do. I'm going to say if my observed z, which was 1.44, had to be greater than 1.96, I would reject the null, but it's not. Let's check the p-value. The p-value of 0.0749 would have to be less than the critical value, or the critical level associated with the significance level of 2.5, so that's 0.025, and that's not less than. So what do? I fail to reject, which in this case is a good thing, because if the company had found out that it had too high a percentage of failed chips or bad chips, it would have to recalibrate the machine. So I bet they're happy when they have a failed test, when they fail to reject the null hypothesis. Now let's look at a final example for using proportion problems, and this is a direct mailing company that sells computers and computer parts. The company claims that at least 90% of all of their orders are mailed within 72 hours after they're received. Quality control takes samples to check to see if this stays valid. So they recently did a sample of 150 orders, and it showed that 129 of them were mailed within 72 hours. So, is the company's claims true? Use a 2.5 significance level to figure it out. Now, as always, we know we're dealing with a proportion problem because we've got all these percentages sprinkled all in here, and nobody even talks about a standard deviation. If we're going to deal with the other types of problems, somebody has to say something about standard deviation. We do not have the population mean, or we don't have the old mean, but what we do have is a sample size. They're taking a sample of 150 orders. They're checking to see if they are mailed within 72 hours. Now, don't let things like this number and this number confuse you. That's just their guideline that they're going by. It has nothing to do with our problem, except for it's the number of hours they have to be mailed within. We're not going to use that in any math. Now the company claim says 90% are mailed within 72 hours. That's going to be their population proportion. That's what they believe they have. So what is my sample proportion? Well, I took a sample of 150 and 129 of them were mailed within 72 hours. Here's how I do my math. I say 129 out of 150 were mailed on time. So that's going to be p hat for me. I say 129 divided by 150, I get 0.86. Now go ahead and figure out what Q is. It's 1 minus P, so it's going to be 0.1. And my significance level of 2.5 is 0.025 as a decimal. Now take a look at what your standard deviation is going to be that you need to calculate. It's going to be the square root of 0.9 P times Q divided by 150. Make sure all of it stays under the radical, the square root sign, and we get 0.0245. Now let's talk about our hypothesis. We're checking as quality control, we're checking to see if the company's claim is false. So that's what we're going to assume. We're going to assume that the company is not right, that at least 90% are not mailed within. So we have to say that we think the mean is less than the 90%. The claim the company makes is that it's at least 90% or greater. So we've got our two hypotheses. Now, because our quality control company, our department works for the company, they're probably hoping that they're wrong, but what they're checking for is to see if the claim is false, to see if their quality control has slipped, and see if they're not shipping as fast as they should. We have to use Z when we're using proportion. We have proportion problems. And this time, we have a left-tailed test, so we won't have to have A divided by 2. Let's set up our rejection region in the left tail. We're going to associate that with 0.025 under the curve. Here it is, 0.025. We have to find out what Z is for 0.025, and we have done that several times already. But if you're just cluing in, here we go. We're going to look on the negative table. We're always going to use the negative when we're looking these up because we're looking for the area in the tail. Even if it's in the positive tail, I'll look it up on the negative side and take the positive value for Z, okay? So I'm going to say 0.025. I found it. There it is. It's associated with a Z value of negative 1.96. And I'm on the negative side of my curve, so I need negative 1.96. So that's what my Z is. Now, what's my rejection rule going to be? Well, I'm going to reject the null hypothesis if I find that I observe a Z value that is less than negative 1.96. Or my p-value could be less than the alpha 0.025. Either one of those would work because basically they mean the same thing. So what's observed Z? Well, I observed a percentage that was shipped on time of 0.86. I think my percentage that is shipped on time should be 0.9. I'm going to divide it by the standard deviation that I calculated. And I come up with a negative 1.63 is my Z value. Okay, negative 1.63, where does that fall? Well, actually, negative 1.63 is not as far negative as negative 1.96, is it? So it doesn't look like it falls into the rejection region at all, does it? It falls over here. Let's see how big this area is associated with that value. And we look up negative 1.63. We can look that up really quick on our Z table. Negative 1.60, 1, 2, and 3. And we have a value of 0.0516. That's the p-value under the curve, 0.0516 associated with it. Okay. Now, let's do the comparisons. If my observed Z, which is a negative 1.63, is less than negative 1.96, I would reject. But as you can see, it's not, is it? And the other check was if the observed p-value, which was 0.0516, was less than the alpha, 0.025, I would reject. But it's not. So both of them failed, which is good. I always like to agree with it so that I know I've checked my work. It's this one, this time we failed to reject the null hypothesis. Good for the company because they can still say that at least 90% of their packages ship on time. Now, the last thing I want to talk to you about in Chapter 9 is just to give you a little guideline, or to tell you where you can search out some information on doing z-test, t-test, and proportion test for hypotheses testing on a calculator like the TI-83 or 84. Your calculator, of course, will be different from the one that I've done the test on probably. So I'm just going to give you some guidelines, and you may have to look this up with Google. But basically, what I want to show you is this screen. These two screens here talk about how to do a z-test. You would input the data. You can give it the mean and the population standard deviation. You could give it the sample mean and the sample size, and then you tell it what kind of hypotheses test you're doing, and it'll come up and tell you some of the numbers that we're looking at, okay? And then you would have that with your test. I'm not going to go into a lot of detail here because this is something that you would play with each of your individual calculators. But basically, you're going to look under the stat function, and under that you would go under the test function, and you would look for z-test for those. For a t-test, these two screens have to do with t-test. You do the same thing. It's under stat, and then it's under test, somehow, wherever your calculator has it. And then, of course, it is the t-test that you're looking up. And the next one is the proportion test, and you would find that under stat, once again, test, and it's the 1 minus proportion z-test. That one's a little more confusing maybe. So it's the 1 minus proportion z-test that you're looking for. Now the proportion, let me just caution you, x here is the number of successes. So sometimes if you're just given the p-hat, if you're given p-hat and you don't have the number of successes, you would actually have to kind of reverse calculate that. And it also doesn't use an alpha level when it's doing these calculations, okay? So they are a little bit different. You will be able to come up with some of the same numbers. You might want to try them with the problems that we've just calculated, see if you can come up with the same numbers, and we'll probably work a little bit more than that in class